Okay, so the next couple of examples I worked out ahead of time, but we're going to continue looking at how to compute eigenvalues and eigenvectors for specific matrices. The one I want to look at right now is the case of a triangular matrix. It turns out that it's actually very, very easy to find the eigenvalues of any triangular matrix, whether it's upper triangular, lower triangular, or remember diagonal matrices are also triangular. So this example tells us how it's going to be done. The eigenvalues of any triangular matrix are simply the diagonal entries. And it's really easy to show that. So rather than kind of prove a general case, you can kind of see from the case of a 4x4 lower triangular matrix like this one. If I were to try and find the characteristic equation, lambda I minus a would look like this. Made a little mistake there, so a little tad sloppy, but notice that this matrix here is also lower triangular. And we know from when we originally talked about these types of matrices, specifically when they came up again in chapter 2, to take the determinant of a triangular matrix is just a matter of multiplying its diagonal entries. So the determinant of that matrix simply looks like this, the product of those diagonal entries. But the solution to this equation when set equal to 0 is just a11, a22, a33, a44, those diagonal entries. So that's extremely useful. We're going to use that fact in the next section where we talk about diagonalizing matrices. But anyways, moving on. So we've talked about how to find eigenvalues for a particular matrix. I want to also talk about something called an eigenspace. So let's suppose that we have an n by n matrix A, and we're looking at one of its eigenvalues. There's a vector space associated with that eigenvalue that we call an eigenspace. Where it comes from, if you remember, the argument that we came up with for deriving that characteristic equation had us looking at this homogeneous linear system. The eigenvectors of the eigenvectors of A corresponding to lambda are the non-zero solutions of this system. And we also know that the solution space, or the solution set for a homogeneous linear system, is a vector space in its own right. We would call that the null space of lambda I minus a, the null space of this matrix. So even though the zero vector is not an eigenvector, if we take the set of all eigenvectors of A corresponding to lambda, and then throw into that set the zero vector, then what you have is the null space of this, which makes it a vector space. We give that a special name. We call it the eigenspace of A corresponding to whatever lambda was. So what I did here is I went back to the example that we did in the previous video where we found the eigenvalues for a particular matrix, a 3x3 matrix. And I wanted to find bases for the eigenspaces of this matrix. There should be one for each eigenvalue that we found. So lambda equals 4. That was one of the eigenvalues that we found here. Now, find that page. Here's where we did that, where we found those eigenvalues here. Remember, they were 4 and -2. And lambda I minus a looked like this. So what I'm going to do is take the eigenvalue 4 and plug it in for the lambdas here. Okay, so that means I'm looking at 4i minus a. After doing that, this is what that matrix becomes. Next thing I want to do is find the null space of this matrix. That would be the eigenspace corresponding to the eigenvalue 4. We know that finding a null space is simply a matter of setting up a homogeneous linear system with this matrix and then solving it. So I set up an augmented matrix where I have zeros here. That makes it homogeneous. And then solving that using Gauss-Jordan, I end up with a row of zeros down here. Now you're expecting to see at least one row of zeros every time. And the reason for that is because if you go back to the original matrix here, we assumed to get this eigenvalue in the first place that this was not invertible. That's where the characteristic equation comes from, the assumption that this won't be invertible. So one of the consequences of that is that when you row reduce this thing, when you perform Gauss-Jordan on this matrix, it should not look like the identity matrix, which is not what we have here. If it's not going to be the identity matrix, then it has to have a row of zeros. So basically, that's an expectation that we get that. It's also important because this row of zeros is going to imply that we have at least one free variable in this system, which we have here. So what I did is I found the general solution to this linear system, which looked like this. x1 is 1/2 t, x2 is 1/2 t, x3 is t. So I have a single parameter assigned to that free variable there. When I write my solution set as a vector and then pull the t out, I get t times 1/2, 1/2, 1. So in other words, the null space of the matrix 4i minus a, which is the eigenspace corresponding to 4, is the span of this vector, which makes this vector by itself enough for a basis for that vector space. So the basis contains this one vector right here. I did the same thing for the eigenvalue -2. I plugged -2 back into that matrix that I showed you on the previous page, which gave me this. Then I created a homogeneous linear system out of this by creating this augmented matrix, row reduced, and got this. Again, row of zeros as expected, which means you're going to have at least one parameter. In this case, we have a free variable here, so I assign a parameter to that. My solution set looks like t 0, or t times the vector 1 1 0. That single vector right there is tossed into a set, and that becomes the basis for this eigenspace. So that gives us a description of the eigenspaces of A corresponding to each of those eigenvalues. Notice these are subspaces of R3. So I have a subspace here and a basis for that subspace here and a basis for that subspace here. Subspaces of R3, you'll recall, always look like either the origin itself, that's the trivial subspace, all of R3, or a line through the origin or a plane through the origin. Any subspace consists of dimension 1, so its basis has one vector, is going to look like a line through the origin. So that's what these eigenspaces look like, geometrically speaking. Okay. One last thing I want to talk about in this section is a really important theorem, kind of illustrating one of the useful aspects of knowing an eigenvalue, knowing the eigenvalues for a matrix. So the theorem says that if a square matrix A is invertible if and only if 0 is not one of its eigenvalues. Or alternatively, if you look at the eigenvalues of matrix A and you happen to see that 0 is there, we know automatically A would not be an invertible matrix. So the proof of this is fairly straightforward, and what it does is it makes use of a property of determinants, but also the fact that our characteristic equation involves a polynomial. So we're going to assume A is an n by n matrix here, and we know that the characteristic polynomial of A comes from the determinant of lambda I minus A, and it always looks like a monic nth degree polynomial, which we've discussed already. Now, what I want to do, again, we're thinking about the possibility that 0 is an eigenvalue. So I want to see what happens if, in this equation right here, if lambda did equal 0. I'm going to plug it into both sides of this. On the left-hand side, if I plug a 0 in for lambda, this becomes the 0 matrix. 0 minus A is just negative A. If I plug 0 into the right-hand side, we know that if you plug 0 into a polynomial, all that leaves you with is the constant term. So on this side, plugging in 0 leaves me with Cn. That reduces this equation down to this. The determinant of negative A equals that constant term Cn. However, in chapter 2, we talk about what to do with a negative in a determinant. In particular, kind of more than that, we talk about what to do, or how, a property of determinants that allows us to pull scalars out of rows of a matrix. So if I multiply matrix A by -1, that's what this looks like, negative A. That's the same as multiplying each of its n rows by -1. If I pull -1 out of each one of those rows, I can bring it out to the front of the determinant, and I'll have a total of n of them, leaving me with -1 to the nth power outside here, times the determinant of A. So now, if I were to take this and replace the determinant of -A in this equation with that, and divide both sides by -1 to the nth power, that effectively just puts the -1 to the nth power over here. And now what I'm seeing is that the determinant of A is equal to basically plus or minus that constant term, depending on what n is. So notice I didn't break this down into two if-then statements. What I wanted to do is just see what happens if I plugged 0 in to my characteristic equation. And what that reduced down to was this. So now we're going to look at the question of invertibility. A is invertible. This is from our equivalence theorem. A is invertible if and only if the determinant of A is not equal to 0. We know that from back in chapter 2. So if A is invertible, then that would imply that this is non-zero, which would imply that this is non-zero, which would imply that the constant term is non-zero. But that can only be the case if lambda is not a solution to the characteristic equation where we set this equal to 0. Notice again, if I plug lambda equals 0 into this, the only way that 0 could be a solution to this is if that constant term was also 0. We occasionally see proofs like this where you have an if and only if statement, but you don't prove both directions separately because each step is what we call an equivalence already. If I did want to break this up into two directions, my proof, for example, if I wanted to say, suppose A is invertible and I wanted to prove that this is not an eigenvalue, then once I got around to proving the other direction, it would look like what I already did, but in reverse. So this is kind of a more efficient way of going about that. This is a useful theorem. Remember this one. We're going to use this again in section 5.2, but that's going to wrap this up.